Yeah, very good morning. Am I audible?
Yes, sir.
Okay. The screen is visible.
Yes, sir.
Okay. So I hope in the yesterday's session in the tutorial, I hope you have seen the one-dimensional heat equation, and the way of solving method is again Fourier method, means using variable separable and okay, and then using initial conditions and boundary conditions properly. Then that will lead to a solution which is of Fourier series type. Okay, so let's continue that. And before going to this heat equation, let me give you a very simple way of solving the wave equation, which is known as D'Alembert solution. Uh, the idea is the transformation. Okay, the transforming the original equation into a more simpler one. Okay, that will be the idea for us by D'Alembert, and he successfully have given a solution for wave equation. Okay, and also the conditions are also verified that f must be periodic with period 2l and so on. Those things will be verified. So here we have this wave equation here. Okay, so if you what is the D'Alembert's idea is he has transformed these variables, independent variables x and t, into new variables v and w. Okay, by using 1-1 onto transformation, 1-1 correspondence, and where he has taken v equals to x minus ct, and he has defined, and w is equals to x plus ct. Later on, we will see what we can do with the initial conditions and boundary conditions. So from here, it's very clear that dou v by dou x and equals to 1 equals to dou w by dou x. Okay. Further, it is also known, it can also derive that dou v by dou t is minus c, and dou w by dou t is c. Okay, so these are easy to derive. Now, you have to transform this utt or uxx into partial derivative with respect to v and w. How would you do that? You are going to use the chain rule. Okay, so you have, this is u is equals to u of x comma t. Okay, but now you have transform it, you want to transform it into v and w, so you can also, because v is also implicit functions of v and w are also function of x and t, so you can also take u as function of v comma w, which is directly, which means you have transformed it. Okay, now from here ut, if you differentiate partially with respect to t, you can use the chain rule that uv, you first with respect to v, then v with respect to t, plus u with respect to w times w with respect to t. Okay, parallelly, I can also perform uxx, because we have to perform, we have to get uxx as well. So ux is equals to uv vx plus uw wx. Now grab the above information. Just now we have derived vt is minus c, and wt is plus c. So if you take, this is c time uv, okay, minus uv plus uw, right? Wt is c and vt is minus c, and this is equals to uv uv plus uw, because vx and wx are 1. Now you again differentiate, okay, with respect to t. Okay, if you differentiate with respect to t, what you will get is utt is equals to, now c time, now you are having uv is a function of v and w, and v and w are function of x and t. So you have to use that information now. C time minus uv partial derivative with respect to v time vt minus uv w partial derivative with respect to, okay. I will, okay, w with respect to t. This is for first term. For second term, uw v vt plus u ww wt. Now this is going to be used now. This vt is minus c, wt is plus c. Okay, so this is going to be c time, now minus minus plus c time uvv minus c time uvw. Okay, now plus c time, so vt is minus c, so minus c time uwv or uvw, both will be the same because you are going to use, assume that u is differentiable, has second order partial derivatives continuous, and so on. Those all conditions satisfied. So that's going to be 2c uvw plus c time uww. So finally, what it will be is, this will imply utt is equals to c square uvv plus plus uww minus 2 times uvw. So this is what you observe from by changing the variables. Now similarly, okay, now similarly, now you have to replace uxx, so uxx, so ux was you have uv plus uw, right? Now uxx is equals to uv v vx plus uvw wx. Similarly, okay, uwv vx plus uww wx. So these all our values are 1. You have, this is uvv plus this is 2 times uvw. Okay, now plus uww. Now you have, this is equation number 2, this is equation number 3, and so now utt is equals to c square time uxx. Use this factor. So utt is c square time uvv minus 2 uvw plus uww, if I recall correctly. Okay, this is there. Okay, is equals to c square time, because c square is sitting outside, uvv plus 2 times uvw plus uww. Now these quantity will get cancelled because they have the same sign on the both side. Okay, and now this will implies 4 c square uvw is equals to 0. So this will imply, since c square is a positive quantity, 4 is a positive quantity, this implies uvw is 0. Now So you have this equation, the wave equation, this, okay, the wave equation is reduced into the following form now when you change the variables. Now, I'm going to ask you what will be the solution of now this equation, okay, UVW equals to 0. What will be the solution of this? You have dealt with a very it's like partial differential equation at least for first order, and okay, I wish to know that whether you can derive the solution for this. Can you give the associated family? Someone can try. Yes. Can someone give try? What will be the possible solution? Second order family. Sorry, second order partial differential equation. Cos part 2. Can you relate number of arbitrary functions?
Two arbitrary functions.
Two arbitrary functions. Yes. So now the two arbitrary functions in such a way that which functions of what? V and W. Now two arbitrary functions will be in the such a form that so that you take first partial derivative with respect to V and then with respect to W or any order. In total this UVW must be 0. So can I give that such a family? That's a U is equals to two arbitrary functions. Let's a function phi plus some function C because I want to make a match with the other further notation. So I'll just take those two arbitrary functions P and C. So can you suggest me what will be the possible functions? The functions of V and W both, or I've given you enough hint.
One can be of V only, another can be of W only.
Yeah. So one can be a function of V only and another one can be a function of W only. Then your purpose will be solved. Okay. Now your job is to now identify what are these arbitrary functions now, V and C. So here this initial conditions and where that the initial conditions will play the role. Okay. So initial conditions, what are the initial conditions was given? U at x comma 0 is f of x, and another initial condition is ut of x comma 0 is c of x. Of course, we are talking about a finite length string. We are not talking about so far infinite length string. Okay. So you have these are the initial conditions. So V and W you know very well. V is x minus ct and W is x plus ct. So they are purely as a function of x and t. So what will be the final shape of u is going to be is equals to u of x comma t. If I want to represent, that's going to be p of x minus ct plus psi of x plus ct. Now use this fact now though. So now this initial condition u at x comma 0 is equals to f of x. This will imply, so replace t equals to 0. What it will give you is phi of x plus psi of x is equals to f of x. It's very straightforward. If you replace t equals to 0 here, so c times 0, this is 0. So say p of x plus c of x. Now, another initial condition, this initial condition. Another initial condition is utx comma 0 is equals to g of x. So you are differentiating with respect to t partially. Okay, use chain rule. Okay, so if you change rules, so phi dash x minus ct time minus c plus c dash x plus c dash of x plus ct times c. Okay, that's it. Partial derivative with respect to t. Now you have to replace t by 0. So these things will go off. So what will be the final one is p dash of x minus c dash of x, or this is plus this minus this, is equals to g of x by c. So you have now two equations. So this will give you, so therefore above implies the following. Above implies that you have phi of x plus c of x is equals to f of x. And another is minus phi dash of x plus c dash of x, psi dash of x is equals to g of x by c. Now, still you can't solve these two equations together because you cannot directly, because here is only phi x and cx and here is phi dash and c dash. So what do? You have to perform the integration for this equation. Okay, on performing integration both sides. Okay, integrate both sides over the limit x naught to x. Okay, x naught is an arbitrary initial point. Okay, so when you do that, so minus integration, you are applying x naught to x phi dash with respect to x plus integration x naught to x c dash of x dx is equals to integration x naught to x g of x by c dx. Now use this. Okay, you know this, these are antiderivatives, right? This is straightforward. You have, this is implies this is going to be phi of x naught minus phi of x plus c of x minus c of x naught is equals to integration x naught to x g of x by c dx. Now you further simplify it. So this will give you, this implies you have a minus phi of x plus c of x. Okay, I'm giving this name phi of x naught minus c of x naught as minus k of x naught, and let's take this is k of x naught plus integration x naught to x g of x by c dx. So what is k of x naught? Is definition is k of x naught is going that side, so you have psi of x naught minus p of x naught. Okay, so this notation is for this. Okay, now another equation is phi of x plus plus c of x is f of x. Now you can solve these two equations into unknowns. Okay, solve these two equations into unknowns, and so how to solve this is you can sum up these two. Okay, you will get psi. If you difference these two, you will get p. Okay, so this will imply, and on solving above, what will it be? What you will get? C of x is equals to 1 by 2 times. Because 2 times C of x is equals to k of x naught plus f of x plus this, right? K of x naught plus f of x plus 1 by c integration x naught to x g of x dx. Okay. Now on difference, if you take the difference, means this minus this. Okay, I'm taking this minus this. So p of x and minus, so phi of x is equals to 1 by 2. So this minus this, right? F of x minus k of x naught minus 1 by c integration x naught to x g of x d. Right? Yes. Now, so you have the definition of P and C now. Okay. Now you can certainly find out u of x comma t now. What is u of x comma t? Is psi of x, p of x minus ct plus c of psi of x plus ct. So replace x by x minus ct here and replace x by x plus ct here and substitute. Okay, you will keep the form. So this is equals to 1 by 2 times. Now f of x minus ct minus k of x naught minus 1 by c integration x naught to x minus ct g of x dx plus c of x plus ct. So c of x plus ct is plus k time x naught, sorry, not k time, k of x naught, okay, because x naught is fixed, so this remains constant, plus f of x plus ct, f of x plus ct plus 1 by c integration x naught to x plus ct g of x dx. So k of x naught will get cancelled. No need to determine this. Okay. And what else you have if you separate these two? So this is equals to 1 by 2 times f of x plus ct minus plus f of x minus ct plus 1 by 2c. Okay. You have integration x naught to x plus ct g of x dx. Okay. Just a second, I think. Right? So if I rewrite the if I rearrange all the things above, 1 by 2 times f of x plus ct minus f, so plus f of x minus ct plus 1 by 2 c integration x naught to x plus ct g of x dx minus 1 by 2 c integration x naught to x minus ct g of x dx. This one. Now, still we can uh, uh, we can composite these two. Okay, so you can just reverse the order. What will happen is this is plus, okay, and what we'll have is here is x minus ct to x naught. Let me change this now. X minus ct to x naught, and this is x naught to x plus ct. So the finally what will you have is this is u of x comma t is equals to 1 by 2 times f of x plus ct plus f of x minus ct plus 1 by 2c integration x minus ct to x plus ct g of x dx. So this will be the final solution. Okay. Now, in case when a g is 0, initial velocity is 0, we have discussed that. Okay. So in case if g of x is 0, You have this is u of x comma t is equals to 1 by 2 f of x plus ct plus f of x minus ct. Okay. Now, if you use the boundary conditions, what are the boundary conditions? Is u of 0 comma t is equals to 0 is equals to u of L comma t for all t greater than 0. Okay. If you use this, what will happen? So u of 0 comma t is equals to 0 is equals to u of L comma t. So u of 0 comma t equals to 0 implies what? 1 by 2 times f of ct plus f of minus ct is equals to 0. If you replace x by 0, you will get this, right? Okay. So what it will tell you, this will imply f of ct is equals to minus time f of minus ct, or this will implies f of minus ct is equals to minus time f of ct. So t is positive anyway, c is positive. Okay. So it says that this implies f is odd. Now the next condition that u of L comma t is 0. So u of L comma t equals to 0. What it will give you is 1 by 2 times f of L plus ct plus f of L minus ct equals to 0. So this will imply that f of L plus ct is equals to minus time f of L minus ct. Okay. Now, since f is odd, you can use that fact now. Okay. So you can use that fact now. So this is equals to f of minus L plus ct. Now, this implies f of L plus ct is equals to f of minus L plus ct. So this will give you, so if you take f of x plus 2L, okay, if you take this f of x plus 2L, this is equals to f of L plus, so this is going to be, I just want to show that this must be equals to f of x. So it is, see, L plus ct is this you have, this equals to f of this is here minus L plus ct minus L. Okay.
So replace CT
So
by
replace
CT plus L.
ct by ct plus L, right? Yeah.
Yes.
So if you replace ct by ct plus L, that will lead to your conclusion. So replacing ct by ct plus L gives us it will gives you that this implies f of ct plus 2L is equals to f of ct. So this shows that f is periodic with period 2L. So f is a odd periodic function. Okay, odd function and periodic. So that's matched with our Fourier series solution that was just now, means we have concluded in the last session that f is going to be a, this f star is nothing but the odd periodic extension of f with period 2L. Okay, right. So this is called D'Alembert solution. Okay, for wave equation. So we have discussed all the things now. So here only changes, I think I've started with v equals to x minus ct and w is x plus ct. So here is just changing the role of v and w. So anyway, you will observe that you will get both. In any case, you will get the following equation. And again, accordingly, this sign will be changing. So you have, this is again, these things are repeated here. So I'm not just leaving it. So you have, this is there. Yeah, fine. Okay. So we have done with the D'Alembert solution of wave equation. So this is for finite length string. What will happen if you have semi-infinite string at least? Means your one end is tied up at 0 and another end you don't know where it ends. Okay. And you have the string is still elastic. Okay. So let's have an example, and we are going to take an help of Laplace transform. Why? Because you have seen the definition of, in the definition of Laplace transform, if you define, so if I recall, the definition of Laplace transform of certain function f of t is going to be integration 0 to infinity e to the power minus st f of t dt. So here it is necessary to define means to define the function f on the positive axis. Okay, so when you talk about the semi-infinite string, you can certainly take the help of Laplace transform, provided some of the conditions are valid. Okay, you have to verify those mathematical assumptions. Now, when you have completely infinite string, means like suppose you have this wave equation is c square uxx, and where you have so 0 less than equals to x less than equals to L previously. Okay, finite length one. Then you are going to discuss 0 less than equal to x less than infinity. Then you may also try to discuss minus infinity less than x less than infinity. Okay, so you will try to go with this. So then, so I just want to give an idea here is that when you talk about this infinite string, infinite length string, okay, you can't use Laplace transform. That's very positive. So then you are supposed to use the Fourier transform. So Fourier transform is going to be is defined maybe in the next session. Okay, and then we will try to use that, okay, to solve the PD and see the applications. Okay, right. So for the semi-infinite string, so let's have one example. Okay, and see how we are going to take the help of Laplace transform. Okay, so we are supposed to find out the displacement of an elastic string subject to the following conditions. The first condition is the string is initially at rest on the x-axis from x equals to 0 to x equal to infinity. Okay, so initially at rest, what does this mean? What are the conditions? Initial conditions are at time t equals to 0, this is 0. And initially at rest means the velocity, initial velocity is also 0. Okay, so this is the first, these are the first two conditions, okay, are assumed. Now, second is for t greater than 0, the left end of the string is moved according to a single sine wave. Okay, so the left end means at the point 0. Okay, so it's moved according to a single sine wave. So w of 0 comma t at x equals to 0 is given. Okay, is moved according to the sine wave if 0 less than equals to t less than equals to 2 pi. So you have this wave equation wtt equals to c square uxx for t greater than 0 and x is 0 less than equals to x less than infinity. Further, as the string is flattened, as the string is going, you are going towards the infinity. Okay, towards the infinity. So displacement is tending to 0. Okay, so this is very much valid or very much required when you are going to apply the Laplace transform. Okay, this is very much required. Okay, it should be tending to 0 as x tends to infinity. Okay, that because when you are going to use the definition of Laplace transform, that is required. So you have these conditions now. So boundary condition is w of 0 comma t is this f of t, and w at L comma L is now infinity. W of x comma t is limit x tends to infinity. W of x comma t is 0 for t greater than equals to 0. So let me write down this model now. Okay. So you have to want to solve this wave equation. Okay. T greater than 0 is fine. And initial conditions is w at x comma 0 is equals to 0 equals to wt x comma 0, and the boundary conditions are w of 0 comma t is equals to f of t. We will see this definition. We can go back and check. Okay, and limit x tends to infinity, w of x comma t is equals to 0 for all t. Okay. Now, if you're going to apply the Laplace transform with respect to t, so because you have to decide, okay, you are going to use the Laplace transform with respect to t variable or with respect to x variable. Okay, so I'm going to use here the Laplace transform with respect to t. Okay, so you have this, what is Laplace transform of w of x comma t with respect to t. Okay, I'm talking about with respect to t, time. Okay, so with respect to time, you are changing into that frequency domain. Okay, so this is equals to integration 0 to infinity e to the power minus st w of x comma t dt. Okay, so t is an independent variable. So we are going to define as this is going to be capital W with x comma s. We are going to define this. Now, if you look at the Laplace transform of wt of x comma t, that's important. Okay, you are taking the Laplace transform with respect to t. This is equals to integration 0 to infinity e to the power minus st wt x comma t dt. Again, so we are going to use the product rule. Okay, you are going to use the product rule, and you can again verify that this is going to be s time w of x comma s minus w at x comma 0. So if you recall the Laplace transform of derivatives, okay, if you recall Laplace transform of derivatives y dash, okay, of x was s time Laplace Laplace transform y, that is capital Y of s minus y at 0. Okay, so you can verify this. Okay, similarly, then you can go for Laplace transform of second derivative with respect to t, and you can verify that this is going to be s square Laplace transform of w, that is x comma s minus s time w of x comma 0 minus wt x comma. I think this is what Laplace transform of y double dash was s square y at s minus s time y dash at 0 minus y at 0, right? Yes. So here is wt, here is not. So you can verify. So now you are going to, so I'm going to use now conditions now. So if you are going to use the conditions, wt at x comma 0 is 0, w of x comma 0 is 0, so it's going to be s square times w of x comma s. Okay. Now what about this case? Laplace transform of, because the right hand side involves the partial derivative with respect to x. Okay, so you can verify, okay, that this is going to be wx comma s partial derivative with respect to x. So this the integral and derivatives can be interchanged. Okay, because you are here, if you look at the definition, because you are taking the Laplace transform with respect to time. I want to add one more line here. That's going to be is equals to this is going to be integration 0 to infinity e to the power minus st wxx x comma t dt. So you can change this integral, means dou square by dou x or dou square by dou x square. You can take it out, and this is nothing but this one, because this is independent of x. Okay, so you can do that. Okay. Moreover, you are again, certainly you are assuming that this w of x comma t is of exponential order alpha. Those all these things means those all the those are the things you can pre-assume those mathematical assumptions here, so that means there is the existence of Laplace transform. Okay, so those part you must take care. Okay, so once you have this, so this is going to be wxx x comma. Now, on using these two, so what you will get is the following. Okay, so using these two, what we will get is the following. So we are going to have s square w w yes, because a Laplace of wtt is s square w, a Laplace of wxx is wxx. Okay, so s square w is equals to c square wxx. Right? So what we will have is this implies wxx minus s square by c square w is equals to 0. So you have a second order differential equation, right? You can treat this as, because s remain fixed, you can treat this as ordinary differential equation of second order with respect to x. And you can certainly identify the solution, say linear homogeneous case. Okay, so you can have this is the solution. You know what is the solution for this? W of x comma s is equals to a times, so what are the roots? Plus minus s by c. Okay, e to the power s x by c plus b time e to the power s x by c with minus sign. Further, you have fixed this s as a constant. Okay, you have taken this s as a constant. So this a and b could be a function of s. They could be functions of s. Not of x, but you have fixed s. You have treated this as an ODE. You have solved this by using the method of linear second order homogeneous differential ordinary differential equation. Okay, so arbitrary constants could be functions of S. Okay, now this is there. Okay, right. So now you are going to incorporate the conditions. Okay, now you have this condition that now at you have the conditions now, right? We have, let's go back and check the conditions. So w of x comma 0 is 0 and w t x comma 0 is 0. Okay, and what is there is w of 0 comma t is f of t. So that tells you this tells you w of 0 comma s, capital W of 0 comma s is capital F of s. Okay, so this certainly implies w of 0 comma s is Laplace transform with respect to f of s. Okay, and this is there, right? And w of x0 is 0. Okay, so Laplace transform of capital W, Laplace transform of this w of x comma 0 is 0. Okay, so similarly here. Okay, so what you will have here is, so w of x comma 0 is 0. Okay, so this implies what? W of x comma 0 is 0 implies what? Is s equals to 0? Okay, so now if s is equals to 0, this e to the power 0 is 1. Okay, and so what you will have is a of 0 plus b of 0 is 0. Right? Okay. Now, what else we can have here is a of 0 plus b of 0 is 0. That's fine. Now, another condition is w of 0 comma s is f of s. Okay, w of 0 comma s is f of s. So this will implies x equals to 0. Okay, so you have a of s plus b of s is equals to f of s. Okay, now we are missing one thing here. Uh, we have used these conditions, right? W of x comma 0 is 0. Okay. Yeah. So yeah, one more information was there. As we have information, right? Limit x tends to infinity, w of x comma t is 0. Okay, so we have this information also. We have to use this information. So Laplace transform of w of xt is w of, so this final value theorem, if you recall. Okay, so that also tells you limit x tends to infinity, w of x comma s is 0. So whenever x is tending to infinity, so this is going to be large value. Okay, because S is greater than 0, C is greater than 0. If x is tending to infinity, this is also tending to infinity, so it exponentially. So this term should be, I mean, that will that should be, that should not take the part, okay, of this solution, okay, to validate this question. Okay, so to use this implies a of s must be 0. Okay, then when this happens, that it in total this will tends to 0 as x tends to infinity. Only then, because this can never be 0 e to the power sx by c, it is going to be exponentially grow. Okay, so to accommodate this condition, limit x tends to infinity w of x comma t is 0, we must have limit x tends to infinity w of x comma s is 0. Okay, and to have this, we must have this a of s must be 0. This arbitrary function, this a of s must be a 0 function. Otherwise, this will grow. Okay, and this is tending to 0 as x tends to infinity. So b of s will not give you much trouble. Okay, whatever a of s will be, so this will have this term will not be involved. Okay, so this implies a of s is 0. So what will be the solution now? Finally, so this above discussion gives us the following. So first thing is, what was that, is w of x comma s is equals to a of s time e to the power sx by c plus b of s time e to the power minus sx by c. Now our discussion tells you a of s must be 0, b of 0 is 0. Okay, further you have this is a of s plus b of s is equals to f of s. Okay, but a of s is 0, so this implies b of s is f of s. Okay, so therefore what you will have is w of, this implies w of x comma s is equals to f of s time e to the power minus sx by c. So you have incorporated all the boundary conditions and initial conditions. Now you can use the inverse Laplace transform. Okay, second shifting theorem, if you recall. Okay, if you know second shifting theorem, if you recall that second shifting theorem, what was that, is Laplace transform of f of t minus a into u of t minus a unit step function is equals to e to the power minus as time f of s. Okay, so if you use this second shifting theorem, then what will give, so this implies w of x comma t is equals to Laplace inverse of f of s time e to the power minus sx by c. So if you a is equals to s by c, okay, so this is equals to f of t minus s by c time u of t minus s by c, s, right, x by c, right, is x by c. This is x by c. You know the definition of f of t now, that is sine t, right? Okay, if you recall, w of x comma t is equals to f of t minus x by c type u of t minus x by c. And what is f of t? Is sine t if 0 less than equals to t less than equals to 2 pi. and 0 otherwise. Okay, right. So this is what the solution of the above semi-infinite string. Give an example. Okay, so we have this is so this is what the final solution. And you can also rewrite this in the following form: sine of t minus x by c whenever this happens. Okay. Right. Now let's look at this example of wave equation now. Okay. So find the solution of UTT with this wave equation satisfying the boundary conditions. This homogeneous boundary condition known as homogeneous boundary conditions. They are both the end theta value is 0 and corresponding to the triangular initial deflection. Okay, so it is given that initially u at x comma 0 is this and initial velocity 0 is ut of x comma 0 is 0. Okay, so you have every information. Okay, so you have to just use the fact, okay, that what was that? The solution. If you recall that Fourier series solution, if you recall, okay, this is the initial deflection. This is given by this. Okay, so initial velocity is 0. So you are not having b n star involving. Okay, so you have this is u of x comma t is equals to summation n equals to 1 to infinity bn cos lambda n t times sine of n pi x by l, right? And what was bn? Bn is nothing but the Fourier sine series coefficient of f. Okay, so this bn, if you recall, what was that bn? Bn is nothing but 2 by l integration 0 to l f of x time sine of n pi x by l dx. And what was lambda n? Was n pi c by l, if you recall that. So all the information you have to substitute. Bn star is 0 because initial velocity is 0. So Bn star is 0. Okay. So these integral you have to solve. Okay. So that I am leaving to you. So here it's given. Okay. Since gx is 0, therefore Bn star is 0 and Bn are given by this formula. So that you can just substitute f of x between 0 to L by 2 have different value. From L by 2 to L, it is having different value. And you have the final one is this. Okay. And you have, this is here. It's given in the final shape. Okay. The final shape is this. So replace Bn by its value, lambda n, you know, n pi c by L, n pi x by L, and you just replace them. So if you have any question, any doubt, you can ask. Yes, any question? Okay, right. So let's move further on. So we have, I think you have seen the one-dimensional heat equation yesterday. Okay. So in any dimension, so this is a Laplacian del square U. Okay. Where C square equals to K by rho sigma. Okay. So we have different names. So I'm just going to recall them. Okay. And so U denotes the temperature in a body of homogeneous material in a space. So X, Y, Z, T. So if you have, so del square U. So del square U is denoted by, means it is nothing but the dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square. Means in the space direction, you have all the second order derivatives except the time one. Okay. So denotes the temperature in a body of homogeneous material in a space. The constant C square is the thermal diffusivity. K is called the thermal conductivity, sigma the specific heat, and rho the density of the material of the body. So these are the separate physical constants which has some meaning attached with the real life problems. Okay, right. So now, so it is here the definition of that L square. So first we will consider the one-dimensional heat equation, bars of finite length. I think that has been discussed yesterday. Okay, so one dimensional means you have here in this case you don't have Y, don't have Z. Okay, so only dou square by dou square U by dou X square. Okay, then you have the heat equation of one dimension. If you include dou square U by dou X square plus dou square U by dou Y square, you have two-dimensional heat equation. If you include all three, you have three-dimensional heat equation. Okay, and so on. T is a time variable. It will not contribute in the dimension right now. However, you can treat that as a one-dimensional extra. Okay, right. So, so homogeneous boundary conditions at the both the end point there is no temperature. Okay, temperature is zero at the both end point. Okay, and initial temperature is can be given by this curve f of x. Then by using these boundary condition, it is easy to determine that f of 0 and f of L is 0 means initially temperature is, it still verify the boundary condition. That's what it means. Okay, right. Now I think yesterday you have seen, so some of you can tell, you have discussed this, right? Some of you can tell yesterday tutorial.
Yes, sir.
So you have discussed this variable separable method, right?
Yes, sir.
Okay, fine. So so again the technique is in this is in the similar fashion what you have seen in the wave equation. Okay, you start with this, you substitute ut and uxx, and then you will find the first order differential equation in G and second order differential equation in F. Use the initial condition and boundary conditions, and then you will arrive at the Fourier series solution. Okay, there will be infinitely many solutions. Okay, so on substituting, you will have the following two equations you have seen yesterday. For non-trivial solution, you must have f of 0 is 0 and f of L is 0. So that can be verified. Okay, because u at x comma 0 is f of x. Okay, at t equals to 0. Yeah, I hope that also has been discussed. U of x comma 0 is f of x. Okay, so this implies f of x into g of 0 is f of x. Now, not that f of 0 is 0. and f of L is 0. Okay, so f of 0 is 0 and f of L is also 0. So see, at initially it is non-zero. Okay, it's a non-zero. So f of x can never be 0 entirely. Okay, and neither z of 0 is a constant. Okay, it also cannot be 0. So to make this condition satisfied, it must be, you must have f of 0 is 0 and f of L is 0 for non-trivial solution. Okay, so from here g of 0 can never be 0. Why? Because if z of 0 is 0, that initial deflation or initially temperature at every point, okay, will become 0. Okay, it can never be 0 then. Okay, so therefore g of 0 can never be 0. Now to accommodate this condition, f of 0 is 0 and f of small f of L is 0. Okay, you must have capital F of 0 is 0 and capital F of L is 0. Then only this condition is satisfied. Okay, so these things can be verified from there. So for non-trivial one, you must have this. So you have two conditions with this second order differential equation, you can solve this. Okay, in the similar one. Okay, and also you can also verify that K must be a negative. Okay, that also you can verify, like we have checked in the wave equation. Okay, and if you solve out all the things, I'm just going with the final one. So here I think we have this, right? So yeah, this I hope you have seen yesterday the following solution. Okay, so following Fourier series solution you must have seen yesterday. Okay, where Bn is nothing but again Fourier sine series coefficient of this. Okay, and Bn will have again the same formula. Okay, right. So I think this has been discussed, so I'm not going through. So the obtained U will be a solution of one-dimensional heat equation under the following condition. F is piecewise continuous, F has one-sided derivatives. Of course, see, when you want to verify this to be a solution of heat equation, you must have first derivative with respect to T partially. Okay, and it should be differentiable 2 times with respect to the space. Okay, so to accommodate those conditions, you must have these assumptions. Here is f is piecewise continuous and f has one-sided derivatives at all points in 0. Okay, so those conditions will take care about it. Okay, rest things are fine because of this exponential function and sine. Okay, so now one example I have. Let's complete it. So find the temperature U in a laterally insulated copper bar 80 centimeter long. Okay, so here it is given L is 80 centimeter. The length of copper bar is 80 centimeter. If the initial temperature is 100 times sine of pi x by 80 degrees Celsius, means it is initially means U at x comma 0, that is f of x, and that is going to be 100 times sine of pi x by 80 degrees Celsius. It's given to you. And the ends are kept at 0 degrees Celsius, means U at 0 comma t is equals to U at L comma t is equals to 0. And the ends are kept at 0 degrees Celsius. How long will it take for the maximum temperature in the bar to drop to? Okay, so first you need to find the solution. Okay, now for the solution you need to find, so if you look at back, so you have all the coefficients here. Okay, all the required data, density, specific heat, thermal conductivity is K. Okay, density is rho, specific heat here is sigma, K by sigma rho. You can find out that's diffusivity, C square constant, K by sigma rho. Okay, so that can be determined from this data. Now, moreover, if you want to determine that Bn, what was the Bn? Bn is nothing but the Fourier series coefficient of Fourier sine series coefficients of, if you recall, let me recall that. U at x comma 0 is equals to f of x, and was that summation n equals to 1 to infinity. You have Bn time sine of n pi x by L. Now here L is 80. Okay, so we have is L is 80. Now what is given is 100 times sine of pi x by 80. So if you compare, okay, it is given to you initially f of x is this. So if you compare, this will implies b1 equals to 100 and b2 equals to b3 equals to and so on, all are 0. Okay, because n equals to 1 will correspond to this, n equals to 2 and so on, b2, b3, b4. There are no more. It's already available in Fourier series form. So you can directly find out. Okay, right? So b1 is 100, b2 is and b3 is 0. Now, what is lambda n? Lambda n was n pi c by L, right? So that is going to be n pi c also can be determined by 80. Okay, right? So here in this case, lambda n was n pi c by L, right? Yes, yes, right. So your solution is b1 time, because b2, b3 and so on 0. So your final solution will be b1 time e to the power minus lambda 1 square t sine of pi x by 80. Okay, that will be the solution. Okay, so what will be the final one here is, so this is there, just now explained. Lambda 1 square is c square pi square by L square. So c square is k by sigma rho. I have told you. K is given to you is 0.95. Density is this rho is 8.92, and specificity is sigma is 0.092. It's all the information is given. So k by sigma rho will be come out to be 1.158. Okay, so lambda 1 square can be evaluated. This will be this one. Okay, the temperature will be 100 times sine pi x by 80 times e to the power minus lambda 1 square t. Okay, now what you want is this temperature to be, you want to determine time, at what time this temperature will be equals to 50 degrees Celsius. So you can solve this. Okay, you can solve this. Okay, so not that this 100 time is equals to 50 implies t equals to 388 seconds. So because this can be maximum value can take 1. So you can replace it, approximately maximum is 100 times e to the power minus 0.001785 t. So you can use that amount here. Okay, and you can identify that 100 times this is equals to 50 implies t equals to this, and 6.5 minutes it will take to reach to 50 degrees Celsius. Okay, right. So I will conclude here. I'm going to give you an exercise now. Okay, you can note it down. The study two-dimensional heat equation. So original equation, heat equation was UT equals to C square time dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square. This is three-dimensional heat equation. Now you consider steady. Steady means dou U by dou T is 0. And you have two-dimensional means this term is not 0. So this term is not going to be involved. Okay, so you have this equation, dou square U by dou X square plus dou square U by dou Y square equals to 0. Okay, now consider a discrete problem in a rectangle R, and here is the assuming that you have the rectangle 0 to A and 0 to B. Okay. So you have a rectangular, so 0 to A, 0 to B. So you have a rectangular shape. Now, this is A and this is B. Now it is given that at any point ux comma b is equals to f of x for 0 less than equals to x less than equals to A, and other everywhere else the temperature is 0. Else there's no, you cannot call this as a temperature, but okay, because it's study equation. Okay, so what I'm giving you an exercise is you start with u of x comma y as a solution as f of x into g of y. Okay, solve this, use this fact and substitute here, and try to figure out what are the type of differential equation you will get. Incorporate these conditions. Try to take the help of Google. There are very much literature is available. Rich literature is available in the Google. Okay, to find out the Fourier series solution of this Laplace equation. Use that fact. Okay, use all these things. Okay, and try to get the Fourier series solution of this Laplace equation. Okay, that we will see in the next session. Okay, thank you. If you have any question, you can ask. Okay, thank you.
Thank you, sir.
Hello, am I audible, sir? Hello.